All right, thank you everyone for showing up to our talk tonight. I want to thank Eli. First off, he has done a fantastic job of organizing this speaker series for the fall. We have some great speakers lined up for the semester. I also want to thank the American Institute of Physics as well as NASA West Virginia Space Grant Consortium. They have helped fund this speaker series over the years. Right now, for this semester, we're being funded by our external donor. So I want to thank them for helping to establish the endowed fund that helps us to do a lot of outreach this past semester and this semester coming up. Without that financial support, some of the things we are able to do, we just wouldn't be able to do. So I do want to thank everybody involved, especially the external donor for this opportunity this semester. So Marshall University is about 8,000 undergraduate students, about 2,500 graduate students. We are an R2 high research activity university. In the physics department, we have several different tracks. If you are interested in some of the physics aspects that you hear tonight, we have a very active geology department as well. So, if you have questions and you're in the area about those programs, don't be afraid to reach out to any one of us here, Eli Williamson, our speaker, Andrew. We'll get you the right information that you need. So we have 5 tracks in physics: the pure physics track, the applied physics track, the medical physics track, a biophysics track, as well as a medical imaging track. These are all undergraduate degrees that will get you a BS degree in physics, but they have concentrations in those other areas. We also have a Master of Science degree, and that's in physics with an area emphasis in teaching, as well as an applied science master's program. So again, if you're looking at a different level, just reach out to us. We'll get you the information that you want to hear about those programs. So there is a Q&A at the end of this. So if you have any questions there, please reach out to us as well. All of our information for our faculty on the physics department with their research websites are online. I encourage you to explore our department. And again, if you have any questions, just shoot us an email. All of our emails are on our website. Mine personally is mcbrides@marshall.edu, and feel free to email any questions you have. I think with that, I'll turn it back over to Eli so he can properly introduce our speaker for tonight.
All right. Thank you, Dr. McBride, and thank you to everybody that's watching right now. This will be the 15th talk in our Faces of Physics speaker series, and I'm quite excited to hear Andrew talk to us about his career as an applied geophysicist. I'll be introducing him shortly, but I wanted to make a few quick announcements. So after this presentation, just like all the other talks, we'll have a Q&A session at the end. We welcome and encourage you to share any questions that you have throughout the talk. If you have anything you just want to say, I'll read that off to our speaker at the end. If you enjoyed this presentation, we hope that you'll join us for future talks in the series. So we're planning on having a Marshall alum speak on November 3rd. Ellie White is her name. This will be November 3rd at 7 p.m. Eastern Standard Time. She will be speaking about her newly attained career as a data analyst for the Green Bank Observatory, as well as some of her previous experiences with radio astronomy. More information about this talk and future talks will be announced soon. So if you'd like to receive email updates about upcoming events, we'll have something in the bottom of the description for this live stream where you can ask to sign up for the mailing list. While you're down there, please consider subscribing to our channel and hitting the little bell icon. That'll let you be notified anytime that we schedule a stream or have anything coming up in the YouTube channel. And if you want to watch some of our previous talks, they'll all be found here on our YouTube channel. So go ahead and check some of those out after our talk tonight. That'd be great. So now it is my pleasure to introduce our speaker, Mr. Andrew Muñoz. So Mr. Andrew Muñoz is an experienced geophysicist who has evaluated seismic for multiple unconventional resource plays across the United States. He holds a bachelor's degree from Texas A&M University and a master's degree from the Colorado School of Mines and Geophysics. Andrew specializes in seismic data conditioning, inversion, interpretation, and multivariate statistical analysis for unconventional resource exploration and development. He is currently the geophysicist for Ensign Natural Resources, a private equity-backed operator in the Eagle Ford Shale play of South Texas. I was first made aware of Andrew through my uncle, David Williamson. I was interested in finding someone to speak who works in the private sector, as many of our speakers recently have been purely academic. And while I feel that academia is extremely important, I also feel that we were underrepresenting the private sector, which is where most, if not all, the application of physics comes into play. So this, coupled with my curiosity about geophysics as a whole, led me to contact Mr. Muñoz, and through the generous donation of his time, we were able to organize and host this talk all within about a month. So a huge thanks to my Uncle David and to Andrew for his promptness and generosity. So thanks again to all of you for coming out, and a huge thanks to Andrew for taking the time to talk about his work during his busy schedule. So without further ado, Mr. Andrew Muñoz.
Thanks, Eli. Appreciate the intro. I'm going to share my screen here. Let's see. It's saying you disabled participant screen sharing. Oops. Okay. So just real quick, my as Eli said, my background is in geophysics, which kind of goes with the title of my career. I was first made aware of geophysics back when I was in college. I was actually initially started as a double major in geology and physics, and then realized that I could actually make a career out of this. So it was neat to be able to step into a major that really spoke to me. And I think what's interesting is that if I probably would have known that unless I hadn't interacted with the geology professors that taught me about geophysics specifically. And so I think that's one of the reasons why I was really interested in giving this talk was I wanted to be able to talk about a career in geophysics, because if your school doesn't offer it, you might never come across it. And in Houston, a lot of people who work in oil and gas meet geophysicists. So it can be a bit regional, but I think a lot of you with physics backgrounds and geology backgrounds would appreciate getting to see a little glimpse into what a career would be like and what kind of things you would do. So just this whole talk is going to be very high level. I want to be able to kind of speak to the high points of being a geophysicist and what we do. And I'll dip my toe a little bit into some topics, research topics that I've been involved in and some of the work that I've done. But in general, study of geophysics is the study of it's one of my favorite quotes here at the bottom, the intensity of waves and fields as they pass through geologic materials. It's one of the easiest ways to describe geophysics. So there's a lot of applications there. We look at earth dynamics where it comes to plate tectonics and seismicity around those plate tectonics, so studying earthquakes. All sorts of natural hazards require some type of monitoring and study. And then even climate science, meteorology, of course, can be a bit more specialized, but in general, in terms of earth dynamics, meteorology is another subject area in geophysics. Most of these subject areas are on the research side, and they tend to be, academics tend to lead them and tend to be in more government type roles like at the USGS. What I'm going to be more focused on today is subsurface exploration. So what I do is my primary job is to explore for and develop oil and gas assets. So the area that I work in right now is a oil and gas asset that's in South Texas, but oil and gas deposits are all over the world. All over the U.S., on land, offshore, in shallow and deep water. So there's lots of places to do this and to look for oil. And the demand worldwide for oil and gas keeps going up year after year, every country. So it's still a very necessary product. Energy helps bring people out of poverty, and we're really proud to be a part of that. The next most common career for a geophysicist would be mineral exploration. Again, bringing the world's energy needs. We need lots of precious metals and lots of rare earth minerals that are quite difficult to find. They don't It's not like you can just dig a hole and find neodymium or find gallium. Well, gallium actually pretty common, but gold and silver and things that we need to run our electronics and to run our car batteries and things like that are difficult to find and require geophysics to help delineate where they are in the world. Another big emerging field is geothermal. It's actually getting quite a lot of traction in my neck of the woods, because a lot of the geophysicists that do work in oil and gas, their skills are directly applicable to searching for geothermal hotspots. And the kind of the final two, hydrogeology does use a lot of geophysics. I'm just going to sort of mention that because it is mostly academic, but I think in the future that it will be another one of those emerging fields that is quite necessary for monitoring fresh water sources as the population of the earth keeps increasing. And then I think finally the most interesting emerging field is the extraterrestrial resource exploration. So whether exploring on planets or the moon or asteroids, which is one that I'll talk about a little bit about, it's still not quite in the private sector yet, because there's not any realistic missions set for the next 10 years or so, but that will be happening really soon. And I think that companies like, maybe not SpaceX, but like SpaceX, who are private and are looking to find minerals will be using these techniques. So on the right here, I'm showing just a diagram of kind of summarizes Earth dynamics. Looking at mantle convection and a lot of geophysicists. There's quite a few academic geophysicists who use earthquakes to actually image the interior of the Earth and give us insights into the dynamics of the Earth and the way the plates move. And same with using satellite data to monitor dynamics of the oceans and dynamics of the climate. And then on the flip side, on the bottom here, we have a picture that kind of helps describe some subsurface exploration. So this is a sort of a cropped cube of a picture of the subsurface, and it's using a method that I use quite a bit, which is called acoustic impedance inversion. And so what we're doing is we're trying to describe the properties of the rocks deep below the subsurface. So these are 10 miles below the surface of the Earth. And those little sticks that are poking out are the wells that have actually been drilled down into that rock formation that's being shown. And the properties of the rocks vary, all around, laterally and vertically. So part of our job is to characterize those changes and to use those changes to look for hydrocarbon and to describe the subsurface. So a little background about me. I think that my pre-professional background is probably the most relevant for this audience, because a lot of you are trying to figure out what you want to do with your careers, what you want to do with your physics degree or maybe geology degree, and I think that geophysics is something you should take a look at. But I got my undergraduate from Texas A&M, as Eli mentioned, in geophysics, and my master's degree from Colorado School of Mines in geophysics as well. And while I had a lot of really great learnings at those institutions and had made a great network, most of my career has been molded by my internships and my actual experience. So my internships, I interned with Newfield Exploration, which is who I ended up getting a job with down the line in Devon Energy. And both of those really forged my desire to go into oil and gas and to solve these subsurface challenges that are extremely difficult. Characterizing the subsurface really is a challenge that takes as much science and as much technology as going to the moon. In fact, some would say it's even more challenging but it's just a lot cheaper to try and fail and to learn. And one thing that I tout as a big contributor to my geophysics career is the Summer of Applied Geophysical Experience. It's a summer program where you go out for, I think it's about 8 weeks. I did this back in 2008, so it's been a while. And that's me driving that vibro-sized truck. And what that truck does is it actually shakes the ground and causes sound waves to propagate through the subsurface, and we measure those back on the surface with a bunch of microphones laid out on the ground. And I'll talk a little more about that. And that experience, it exposed me to all types of geophysical acquisition techniques, and it gave me the background of actually going out and acquiring the data and then processing it and then presenting it and understanding it, and getting to see all the different geophysical techniques made me really fall in love with the subject and just solidified my my experience. And then it was also a great resume booster. People who are looking for candidates for jobs really love hard experience, like experience working, learning, even if it's ancillary to what you're actually going to do. My primary research at Colorado School of Mines was centered around utilizing dynamic time warping. It's not direct applicable experience, but the results of it were directly applicable to what I was doing, what I ended up doing in my career. And so it was a useful skill. I learned how to program. I learned I learned Python and Java, and I learned how to actually apply my research to real data that we use, the same type of data that I use every day here now. So having that research was really important as well in growing my career. So the types of industries that you'll see geophysicists go into are, I think, primarily oil and gas exploration. That's one of the biggest careers for geophysicists. And we use seismic data to characterize the subsurface, as well as well logs, which basically take physical measurements inside a drilled hole. And I put CCUS on the end here, which is carbon capture, utilization, storage. And that is an emergent field where we take compressed CO2 and pump it back into old depleted reservoirs that can actually house it and retain it. And that's becoming really popular as a method to mitigate climate change. The second most popular is mineral exploration, looking for precious metals. The interesting thing about mineral exploration is they actually try to use just about every geophysical tool they can get their hands on, whether it's looking at potential fields, which would be looking at changes in gravity and magnetics, measuring electrical field changes and inducing those into the ground to see if that causes certain minerals to light up, and then as seismic as well, inducing acoustic waves into the earth and looking for the reflections. Water mapping typically uses electromagnetic or induced potential methods, which are induce electric fields into the earth, and those electric fields can image the conductive water reservoirs below them, or in some cases resistive if they're really fresh. Geothermal, again, is really emerging, also uses seismic, which is why a lot of oil and gas geophysicists are going into this field, and then magnetotelluric methods, which are looking at the changes of the Earth's electric field over time. And then finally, extraterrestrial methods are right now off of satellites. We're mostly using radar and hyperspectral imaging. And of course, as we put rovers on Mars and the Moon, we'll be doing more direct measurements similar to what we do on Earth. Okay, so my professional experience. The company that I work for, we actively drill horizontal wells in South Texas, south of San Antonio. I've been able to drill wells in Utah, offshore Gulf of Mexico, in other exploration plays in Oklahoma. And so there are like I said, oil and gas deposits all over the world, and depending on which company you work for, you can work in almost any of them. And so we primarily work with three-dimensional seismic data, which is I'm going to talk a little bit about. It's basically constructing a three-dimensional image of the subsurface or of the ground below you using acoustic waves, using sound waves that you induce into the ground. Right now, a lot of my focus is using data science and you heard some of my background in multivariate statistical analysis, and using data science to actually merge geoscience data, which is of a very unique form, to engineering data, or data that we actually get from producing oil and gas, and from actually inducing hydraulic fractures into reservoirs. And so merging that data is really valuable in helping understanding where oil deposits are and how much you can actually produce from the ground. So on the top right, this is just an example from, I don't have a lot of examples because most of the data is proprietary that I work with, and I can't actually show it in public. But I did have a publication out, I occasionally publish about 2 years ago. And so this was some work that I had taken some older seismic data that had been used, that had been merged from a processor who was just trying to get it out and sell it quickly. And so we cleaned it up and made it really usable for doing fine-tune, enhanced imaging and exploration. And the left is just showing the initial state of the data. And the right is after I cleaned it up. And so those little wavelets that you see are the reflections of the sound waves coming off the rock layers. And this is quite deep in the ground. This is almost 12,000 feet in the ground. Almost over 2 miles. And then on the bottom right, this is actually an image from one of my colleagues from mines, Xinming Wu, who's now a professor, and he I just thought it was a beautiful visual description of seismic interpretation. So looking at these images and actually interpreting the horizon, which would be the top of a rock layer, and looking at faults, which on the surface we see faults as faults typically occur, along they form rivers, and they're basically just displaced rock, and when they move, it's what causes earthquakes. So there's lots of faulting in the subsurface, and oil and gas deposits are typically trapped up against faults, at least on a conventional sense. At the very bottom, there's these salt bodies that are imaged. So there's a lot of really interesting imaging and a lot of really interesting visualization that you get to do with 3D seismic data that you don't really see in a lot of other industries. And so there's a bit of artistic flair to when you're looking at this data and when you're using this data. And so it can be kind of fun to get to dive into that and put your own interpretation on the data. So just a quick primer so you have some understanding. Seismic data is essentially using acoustic waves. So you create a pressure source at the surface of the earth, and you wait for the sound waves to propagate through the earth, and the sound waves bounce off of reflections in the subsurface. So these reflections are created by different rock layers and changing rock layers. So each rock layer has its own mechanical properties. It's got its own speed at which sound travels through it. It's got its own density, and so these properties are that are related to velocity and density, or what we call impedance. And so we look for those contrasts and build the seismogram to create this image. And you do this millions of times over every point in the earth which you're acquiring the data, and you can come up with a three-dimensional image of the subsurface. And ultimately what we look for is the petroleum has kind of a special contrast that we look for, and that is how we use the data to actually find petroleum. And where we know there's petroleum, where we have what's called a source rock, or a rock that generates hydrocarbon, which is what my company is currently targeting, we can use this data to actually map the subsurface structure, because usually there's a lot more elevation changes. You've got giant canyons and reefs and all sorts of things that have been buried for millions of years that we drill our wells into and that have hydrocarbons. So knowing how and where to drill down, 2-3 miles into the earth, and then being able to turn that wellbore and actually drill it horizontally takes a lot of knowledge of the elevations and the changes that are occurring deep underground. So if you look back at this image again, you can see there's a lot of elevation changes, and this is probably not even vertically exaggerated to what's actually going on. I think it's a little bit less exaggerated. So onshore for actually capturing this data, on the left side, I'm showing kind of a picture for onshore acquisition. And what you do is you just lay out these microphones in long lines, and you generally drive a truck around that a specialized truck, the Viber size that you saw in the picture of me driving above, and it shakes the ground, and you create those sound wave sources, and then you collect the reflections as they come back up from after the sound waves travel all the way down and then come back up. And then the same thing happens with offshore exploration, except for you just drive a boat and you use air guns. The air, you can actually shoot air bubbles fast enough through the ocean all the way to the ocean floor, fast enough to create waves that propagate all the way down into the deep part of the subsurface below the ocean. And same thing, we use that data to create this image. So just high level, it's fun being able to take this data, use it to look for oil, use it to drill wells, and be a part of a multidisciplinary team of geologists and engineers that do this. And it's a really fun, rewarding career. The puzzles and the challenges are really really difficult, and you'll have a lot to think about and a lot to do every day. So just kind of I wanted to give sort of a summary of what it's like to have the career in oil and gas. And typically you need to have a master's or a PhD in geophysics, physics, or math. Preferably geophysics, obviously, if you're going to do geophysics, but physics is pretty close to it. If you're doing an undergrad in any of those, then it's very easy to go and get a master's in geophysics or a PhD in geophysics. It's best to have some experience with seismic processing or interpretation. Having a background in geology helps, although it's not required. It just helps give you understanding of what you're actually imaging when you're doing this, when you're working with this type of data. Nowadays, I think being able to program, preferably in like an object-oriented programming or Python, is extremely valuable. That's one of those things that I think coming out of school, anybody who's in physical sciences who wants to do applied science needs to learn how to program. Industry experiences and internships are something you should go for and just try to get out there and get, because that's super valuable. Being a seismic interpreter or processor and an EMP, that's kind of what I do. I'm very ingrained in the day-to-day and the drilling of wells and trying to figure out where and what we're going to do next. You're very much ahead on the planning. You can also be a researcher at a major exploration and production company. So there's still a lot of research in seismic imaging and trying to understand how to make better images, make more accurate images. So major oil and gas companies, pay researchers just as much, just as well, or sometimes even more to come in. Mostly, you typically have to be a PhD to be able to do this. And come in and do research for them and do work on really difficult proprietary problems that help make them better producers. Of course, there's always an academia route. There's lots of great schools for geophysics, and I encourage you to go out there and look for some. Most of the time, the jobs in oil and gas are going to be centered in Houston, Oklahoma, so Oklahoma City or Tulsa, in Denver. And I've actually worked in all three places, and I can say, all three places are great places to work. However, I mean, if you want to work for a large oil and gas company, there's jobs all over the world, and there's oil and gas deposits all over the world. So there's lots of great places to go and work. Most of the time, you're going to be working in the office, but there are some jobs where you can actually go out on seismic acquisition ships and get to ride around and see lots of parts of the world. Geophysicists at oil and gas companies, to no surprise, get paid really well. Starting salary for most are around $100,000 a year, and they have really high upward potential. It climbs from there, and there's it's a very good industry to be in. You're treated very well, and there's a lot of really good people in the industry, and it's something that I would encourage everyone to look into. So on the mineral exploration side, as I said, geophysicists use a variety of methods, whether it's capturing the changes of potential fields like gravity, gravity changes, so changes in milligauss or acceleration like throughout areas. You can tell I don't spend a lot of time looking at gravity data, or looking at changes to the magnetic field. Those are to the Earth's magnetic field. Those show quite a bit of character and can tell you give you evidence of where mineral deposits are. You can also induce electric fields. That's popular for looking for conductive minerals, especially, or especially resistive minerals that are in conductive settings. And then and seismic as well, if you're looking at areas that have some type of complicated tectonics, like faulting and layers that are difficult to see from the surface. I like to use Australia when I talk about mineral exploration, because they do a lot of mineral exploration and they publish a lot of geophysical data. So a lot of it's freely available online to just go and look at and download. But there's a lot of really interesting data here. You can see that Australia has over the continent has the majority of commodity metals that we would need around the world. So what a potential field map looks like. So on the left, this is data that's acquired basically from an airplane. They tow magnetometers and gravimeters across huge swaths of areas, and of course that can be done from drones. It can be done from the ground. It all depends on the type and resolution of data and depth of data that you want to acquire. So the height typically corresponds with the depth that you're looking for. So with magnetometers, it helps highlight faults. It helps highlight magnetic formations. And it's one of those tools that can be used to cover large areas and map out mineral deposits and map out settings for mineral deposits pretty easily. And again, typically they use a triaxial magnetometer that measures the changes of magnetic field, three vector directions. With gravimeters, this is a kind of the classic gravimeter. It uses a zero-length spring, and what you're looking for is just changes in gravity. And ultimately, what that is changes in density across different areas. And so you can see really dense minerals, you can see really dense deposits, or you can see areas that have a lot of sediment cover and have a less dense setting. So, but the mineral geophysicists who do mineral exploration will combine these techniques and use them for looking for very specific minerals and where they know they're going to find them. So some look along faults, some look in with certain types of formations that are near the surface. Some try to map the formations in the subsurface and then drill down to meet them and dig mines to capture them. So mineral exploration, it's not too dissimilar in terms of skills from doing oil and gas. You can start with a bachelor's. I've seen quite a few entry levels with a bachelor's of geophysics, but I think more and more nowadays, companies are wanting people with at least a master's degree. And again, you have to kind of be a Swiss Army knife of geophysical methods, because being able to look and being able to acquire and analyze gravity, magnetics data, electromagnetic data, seismic data, and being able to interpret all that is something that these guys value a lot. It's good to have a background in mining, since you're going to be doing you're going to be searching for minerals that will ultimately be mined. Again, it's one of those fields that there's a lot of creative ideas that you might have, whether it's the way you combine the data or how you analyze the data. And so having programming skills is really valuable, because in this field, especially in the field of mining, there's not as much commercial software as there is for oil and gas. And it's really good to be able to create your own tools and process the data the way that you're thinking of looking through it. Again, hard experience is really valued, since this is in a very industrial field. And it's mostly mining companies that are hiring people out. But of course, what's interesting about this, I think one of the most interesting things about mineral exploration is that you get a lot of field time. So you get to spend a lot of time out in the field because you're doing a lot of different acquisitions at different heights and frequencies from the surface. There's jobs all over the world. Mining is occurring all over the place, and it's not as centered as oil and gas is. And then, of course, there's many positions available in academia, especially for people who specialize in one of these remote sensing methods. Mining, geophysics jobs at mining companies have caught up recently with oil and gas salaries. I've been seeing entry-level salaries between 80 and 100 and plus. So it's another job that you'll be able to jump out into and make a good salary, make a good living, and get a lot of really interesting experience. So one of the emerging fields, geothermal exploration, is hiring quite a few geophysicists. So on the left, SMU, Southern Methodist University, they're in Dallas. They have a heat flow map across the entire U.S. They use well data and other types of measurements to create this, and this shows the extent of warm crust that can be utilized for, or high heat flow crust that can be utilized for geothermal exploration. And what's interesting is that in South Texas, so my field is actually right along this big old hotspot here. We produce wells. I'm not sure if my cursor could be seen. I hope it can. We are producing wells along this area, and part of the reason the oil and gas is there is because over time, when those organic substances are deposited and buried over millions of years, and they undergo heat and pressure, that heat generates a lot of those hydrocarbons. So having extra heat flow helps generate more of those hydrocarbons. But through the Southwest, there's quite an extensive amount of heat. And then, of course, on the Western US, where you have thinner crust, you get a much higher heat profile that in Oregon, so this is actually the Newberry volcano, but there are other spots in Oregon that people are looking at. Zongi or Zonge, I'm not sure how you pronounce it, but there's a company that's looking at geothermal projects all around the US. And I thought this was a really interesting 3D model, one of the best ones I've seen for magnetotellurics. So they created this three-dimensional model using magnetotelluric data, and so they can actually image the top of the volcano and then image the hot area, the warm areas of the crust that they want to inject water into and flow it back for geothermal sourcing. So this is a really interesting field. It's the oil and gas industry is kind of getting into this, especially using old well bores. So looking forward to seeing how geothermal evolves over the next 10 years or so. Now, a really interesting field is extraterrestrial exploration, especially for resources. We know that during the formation of the solar system, it's likely that asteroids and other extraterrestrial hard rock bodies have a significant amount of minerals and resources that we would use on Earth. And if they can be safely extracted and mined and brought back, then that would be very valuable for humanity. It could advance humanity in ways that we haven't imagined. And so there's a lot of research focused on this area. Funny enough, one of my professors at Mines was in a group that did a feasibility study on imaging an asteroid. So they used this setup where they had a satellite that was pulsing radar, and it was orbiting this asteroid at from a non-circular orbit, because the asteroid was asymmetric around a three-dimensional asteroid, and was pulsing radar at it. So this is a common technique that we use on Earth as well, called ground penetrating radar, except for this is in space. And so you're basically pulsing electromagnetic waves, and so like low frequency, like microwaves, low frequency electromagnetic waves that behave just like acoustic waves. So very similar to acoustic waves. So instead of measuring impedances, you're measuring, I'm blanking out. You're measuring the dielectric constant. I'm going to get killed for not remembering this. Of the dielectric changes on the interior of the asteroid. And so if it contains precious metals, anything that has a different dielectric constant outside of silica rock, basically, you should be able to see it. You should be able to image it. So he worked on a really interesting project that published, I think, 3 or 4 papers describing this theoretical experiment. But in reality, this is going to be part of our future. So it's most of the jobs I've seen, and actually Colorado School of Mines has a great link here, and I can put this down in the comments, or give it to Eli to put in the description, about asteroid space mining and what resource jobs you can actually find nowadays. And most of them are on NASA or military, but I think that that's list is going to grow as we see the potential for this resource. And so finally, to summarize in general, I wanted to leave you with a few career tips. One of the most important things in my career, and I've said this to many people, is to collect and utilize mentors. And I say collect because it's kind of a harsh term, but get as many mentors as you can, and use them and call them, and use the resources they have, use the knowledge they have, because that is one of the best and most efficient ways of learning. Even if you need to cold call somebody, you gotta pocket a lunch or coffee. And of course, if somebody's in private industry, they'll probably pay for your lunch. But one of the best places to find them is during internships or to any type of industry experience. And I can't emphasize that enough. I just think that's a very important resource for students, especially, and early career individuals. The other thing, I've hit on this already, learn to code, learn Python, learn R, whatever speaks to you. It's so important for applied science. And it's so important to be able to create your own custom tools, to be able to create software. And I can't encourage that enough. And then finally, go out and actually get some experience. I love research. It's great. You can do some really cool things. You can deep dive into some great topics. But even if you're doing a PhD, go get some experience in industry. You'll learn a lot. You'll get a different perspective. You might come back with a different view on your own research. but get internships, travel to them if you can, and try to get these applied experiences and branch out. Internships in oil and gas generally pay pretty well. Unfortunately, don't have a lot of information about internships in mineral exploration or at NASA, but I imagine they have at least some type of grants or some type of help to that will so you actually be paid and be supported during those times. But thank you everyone for your time. I'd be more than happy to take questions, and I'll also hop in every once in a while and answer some questions in the comments for those who come back and watch this later.
All right. Well, thank you very much for your time, Andrew. So I've already got a couple of questions up in the chat here. This first one comes from my wife, Julia, who always watches these.
That's really nice.
She wanted to ask, have you always been interested in geology and physics, or was it kind of one after the other while you were growing up?
Yeah, that's a great question. When I got interested in it was it wasn't in college. It was actually in high school. I participated in a program called National Ocean Sciences Bowl, and I believe they had a hiatus and it picked back up recently. And it was there that I was like the geology member of the team, and so I just studied it and learned it, and so I was really interested in it, and I was already really interested in physics in high school, just from a being interested in science in general. And so when I went in, I really wanted to try to do both, and I didn't really learn about geophysics until I was actually took a couple courses in college, and I think it wasn't until my sophomore year that I had any idea about geophysics or oil and gas or anything. My interest wasn't even in oil and gas initially. I mean, I had interest in potential fields and electromagnetics. I thought it was really cool and really interesting. But then when I got to learn about subsurface problems, especially in oil and gas, that's what kind of hooked me.
Awesome. Okay, so we've got two questions from the same person here. It's either Matthew Schaefer or Matthew Schaffer. The first one says, what would you say to students who may be interested but find geophysics intimidating?
If you're already in physics, I'd say it's not much more math, or actually it's probably less, to be honest, probably less math. And there is a lot. You're going to cover a breadth of topics, but it's one of those things that once you get into it and once you start to really enjoy the subject area, it'll get easier and easier for you. So if you can handle, college physics up to kind of like modern physics, or where you're learning about thermodynamics, or you're learning about kind of basic EM magnetics, it's really not that difficult. And if you go into oil and gas, it gets even easier. I would say that there's parts, I talked a lot about the subject area, but I spend most of my time doing a lot of interpretation, work with engineers, and it's so applied that it's not like I'm going out and deriving things and writing equations every day. So I think if you can get yourself through the education, it's a really fun career, and it doesn't require that you have to be like a math wizard or anything.
All right. And the second question for Matthew here. How do you see the future landscape changing in the industry due to the impacts of climate change?
Yeah, that's a good question. We talk about that a lot. The reality of our world is that our population of the world is growing. It's requiring more and more resources every year, and those resources are becoming more scarce. And unfortunately, while I think a lot of people around the world have this hopefulness that we can be completely independent of fossil fuels, oil provides power for most of the power in the world, oil and gas, and so we're still very reliant on that. Emerging developing countries are relying on that. They're relying on the energy to get out of poverty. And the energy density of hydrocarbons is just so vastly greater than all the other technologies we have now, except for nuclear, that it's hard to get ourselves off that. And then in addition to just energy, we're completely dependent on petroleum for plastics and medical devices and medicine. And a lot of the modern amenities that we enjoy, in fact, almost all the modern amenities that we enjoy are reliant on oil. So it's one of those things that, we as an oil and gas industry, need to continue to get better and need to continue to be environmentally conscious of the areas that we impact and our impact on the world. And I think people will be surprised to see how much the people in oil and gas companies really care about that. We're outdoorsmen. We're ones, we want the environment to be preserved and sustained, and have no interest in ruining it. And so everything that we do, we want to make sure that that stays true. So I went off on a bit of a tangent there, but it's all related somehow.
I think it answered the question well. Okay, so I'm not seeing any more questions popping up here.
So I got one. So I understand the importance of the internships in the industry. How many would you say that you participated in versus maybe the academic research side of things? So what was the balance that you went through?
Yeah, so I spent my undergraduate, I tried to get them as quick as I could. My first year was not very successful. I think I was a little young for it. And that's when I went to the Summer of Applied Geophysics experience. But once you're kind of a junior, senior, and undergraduate, that's a good time to start looking and trying to get out there. I did both my junior and senior year of college internships over the summer. And then when I was at Mines, even I was actually in the PhD program for a good little bit, and I just tried to balance. I found the internship so valuable that I tried to do that every summer, and then try to just balance my research during the year. And ultimately, I decided the PhD program wasn't really for me, and got back into industry. But even the academics, the ones who spend their time, trying to finish their thesis and trying to get research done. Honestly, most of them, they only do that once, and it's usually at the end of their PhD when they're really trying to make that final push, or if they just kind of time their second comps out or something, where they have to, really get in there and prepare it. For the most part in geophysics, it's that valuable that you want to be trying to do it every summer.
Okay, had one more question pop up here. It's from my sister Faith. She said, I think it was called CCUS, but I'd like to hear more about it. I remember you saying that you basically put oil back somewhere. Is this a regenerative type thing, or just kind of putting it somewhere to keep it from harming the environment?
Yeah, that's a great question. So what you do is you take, however you get the CO2, whether you capture it from power plants or whether you capture it from out of the air. Occidental Petroleum has a big program where they have these big fans where they actually pull it out of the air. However you capture the CO2, you compress it with a big compressor, and that makes it into like a liquefied form. And then you actually pump that CO2 gas down into an old oil well, so an oil well that's not producing anymore, or a well that you specifically drill to inject into. And what you do is you inject it deep down into a reservoir that's already been had oil pulled out of it. So what happens with oil is that when it generates in the subsurface, it causes this overpressure underneath the earth. And so that overpressure, once you poke a hole in it, it wants to flow out. And so once you flow it out, then it's got an underpressure because you've taken all the fluid away. So you can pump in CO2 in a supercritical state, and then it will actually increase the pressure again. And you can fill up the reservoir from that depleted pressure, or where the depleted pressure is, and it just indefinitely stores it. And then once you're done pumping it in, you would just cement the well bore and leave it there. And
That's
you do
really
what's called a plug and abandon. So you put a big put a big cast iron plug way down, and fill up the backside with cement. Yeah.
I like it.
And then actually a lot of times what we do is we actually cut the well. You actually dig a big hole around the wellbore, you cut it and you cap it, and then you bury it back so that you can restore the environment around it too.
Well, it certainly sounds like a really cool process. I have never heard of that before. And what was it called again?
CCUS, carbon capture utilization storage.
Okay.
I think it's carbon capture utilization storage. I'm probably quoting it wrong now. Yeah, carbon capture utilization and storage. Yes, it's just the process of injecting it and permanently storing it. You can think of it like the Yucca Mountain project, where they're taking industrial waste or nuclear waste and storing it. It's not happening, but storing it indefinitely, right, under Yucca Mountain. That's kind of a similar thing, except for it's buried beneath so much so many layers of rock that there's no way of it coming out unless it goes out on the wellbore or something. So
that's really cool.
That's actually another, I didn't mention that. That's actually, so in parallel to CCUS, taking old wellbores and putting radioactive waste in concrete containers and putting it down the wellbores and then sealing the wellbores. That's another way of actually disposing of nuclear waste that's being looked into as well. Because you're so far below like any water or anything like that when you're drilling oil wells, that it's a really good place to contain any type of hazardous material.
Okay. Well, so I don't think we have any more questions coming in. Dr. McBride, do you have anything else?
No, I think that answered my questions.
Okay. I don't think I have anything else. So we've got a thank you coming in from Matthew Schaefer for answering his question earlier.
Thanks, Matt.
And so I would like to repeat that sentiment. Thank you very much for coming out to talk with us today. I think it was very informational, and I hope that we can get some more people interested in geophysics and maybe have some people join SPS talking about that. I think it'd be pretty cool.
Yeah, absolutely. And I mean, if anyone's looking for a career and they want some really specific advice or has a question, about what they're doing, find me on LinkedIn and send me a message and I'll answer it.
All right. I think with that, we will go ahead and end the stream for tonight. Thank you, everybody that had questions, and thank you for everybody that watched. And of course, thank you, Andrew. I really appreciate you spending the time to come out and do this tonight.
Thanks, Sean. Take care.
All right. That's the end.